How's everybody doing? We have a second chance at glory. All right, so this time we installed like some stuff to catch the bottles. We think the plastic might have frozen from the liquid nitrogen and then cracked when it hit the bottom of the can. So we have insulation in there now, so here we go. It's pretty loud, apparently. He said, so Patrick, who's the guy who does all the prep, he said he was surprised he didn't hear it upstairs. He said he knew something had gone wrong. And also, liquid nitrogen, I discovered, anyone have like closed-toed shoes up here? Yeah, okay. So I discovered if you throw this like across the floor, it sort of makes pebbles. I'll do it on both sides, and it skates across the floor. Here, I'll do it again for you guys in the back. It hovers on the surface of the floor because it's vaporizing so fast. Oh wait, hold on, that wasn't a good one. There we go. It's sort of like water on a hot stove. And everybody have shoes that are good? All right. Yeah. Here, you want some? Yeah. So very cool. All right. Stop dilly-dallying. All right. I've never done it before. Again, it should take about 30 seconds. Oh my God! Finally, we got a good demo. Wow. So here I can show you the damage. So the bottom is completely gone off. So the power of expanding gases and pressure, pretty cool. I'm really pleased that that actually worked. And yes, I requested it again because I was not going to let it slip by me this time. All right, so also in emails last night, I sent out forms for both the Makerspace tour. We have about 60 signups, so if anyone really, really wants to do it and hasn't signed up, there's probably like 5 or 6 spots left. That'll be this Friday, so I'll end class about halfway through. Also, I sent out the much anticipated Class Olympics form. We have about 75 signups so far, so that's looking really good. Also, whoever has a spike ball net, you are a godsend because we are going to be playing spike ball. That is a 100% certainty. All right, so first law. So last time we talked about the ideal gas law, which was all about the pressure, volume, and temperature at any given instant inside of a gas. And again, you sort of knew a lot about that from chemistry, but this is like more of a physics viewpoint on it. So now we're actually going to use the ideal gas law to talk about temperature changes due to injecting energy into things. Okay. All right, so heat versus temperature. Again, I think this is something that's more or less covered in chemistry. Heat and temperature are two different things. And specifically, heat is the one that's easy to define. It's like energy transfer in the form of thermal energy. So heat is energy. Literally the one time I don't do the squiggle thing, the pen stops working. I'm writing in white, but I'm stuck. You cannot be serious. You actually can't make this up. I've done the squig. You've seen me do the 2 squiggles every single class to make sure the pen works. This is the first time I have not done it.
Tragic.
It is tragic. Okay. We're going to the emergency pen. There we go. All right, so heat is energy. Temperature is not energy. And specifically, heat is energy in the form of like thermal energy. It's kind of circular to define anything. Thermal energy is heat, heat's thermal energy. All right, and temperature actually, even though we use it every day, it's actually pretty strange. So you've probably heard the definition of it's like average kinetic energy per molecule, that's a decent definition. Really, the best definitions of temperature involve something which we'll learn about later called entropy, which actually you know a little bit about from chem, you know, like K log W. So the best definition of temperature is actually like a conversion factor between heat and energy, but that's very like strict and formal. What we're going to use is temperature is like objects of different temperatures will exchange heat in a certain direction based on which one is higher temperature. So objects of different temperatures exchange heat energy until their temperatures become equal, and at that point they do not exchange heat anymore. And obviously the object giving the heat loses, or its temperature decreases as it transfers its thermal energy out, and the object into which the heat is being transferred has its temperature increase as it absorbs energy. Yes?
Is it a constant?
Is what a constant?
Is temperature a constant compared to?
No, so temperature is sort of like, it's roughly like a measurement of how much energy is in the object averaged over the number of molecules. It's similar to average kinetic, like atomic motion energy per molecule. So I guess I'll write that down. It's sort of like thermal energy stored in each molecule in the form of like the Brownian motion, like the vibration kinetic energy. Okay. Again, temperature, you don't really need to define it. It's pretty, you understand what it is at an everyday level. Okay, and just as an example, so I was the lab TA last semester, and a lot of people were saying, have you guys done the lab yet with liquid nitrogen? No, okay. So in liquid, you're going to actually get to play with this stuff. So you're going to pour it into a cup and have it evaporate. And a question is, where is the energy coming from that's causing the liquid nitrogen to, well, boil, I guess? And people were often saying it's the temperature from the air. Now, strictly speaking, that's not true. What's happening is the air is a higher temperature than the liquid nitrogen. Therefore, the air transfers heat energy into the liquid nitrogen. As the liquid nitrogen receives the heat energy, its temperature increases. Okay, so they're not just transferring temperature to each other. Because of their temperature difference, they're transferring heat to each other. So temperature difference between air and Ln2, which is a symbol for liquid nitrogen, causes heat transfer. Okay. And the heat transfer is the actual energy that's going from one object into the other. Anybody need more time to write? All right. Okay, we're going to talk also about work now. So the first law is going to relate heat, work, and like thermal energy / temperature, I guess, but thermal energy. So we just covered thermal energy. Now we're going to do a little bit about work, and we also did heat. So just some reminders from Physics 1. When work is done on an object, that is an injection of energy into it. It increases the energy of the object when you do work on it. Okay, and the internal energy goes up. An example would be if you push a box up a hill, you are doing work on the object and you're injecting energy into it and it's being stored in the object's potential energy. Or if you push it on flat ground, it's being converted into additional kinetic energy of the object. So a familiar example would be pushing a box. And either up a hill or flat ground. Again, that's just to emphasize that you can store that energy you injected as work either as potential energy or kinetic energy of the object receiving it. It depends on the situation, but it'll be pretty obvious. Okay, if an object does work on its surroundings, it's spending its built-up energy. And therefore, its remaining internal energy goes down. This is a little bit tougher to have like super familiar examples. I had one that I thought I would remember immediately. Well, okay, so I guess we could use the stored energy in a spring. So although the spring potential energy is a little bit harder to understand than potential energy. As a spring is compressed, it has high potential energy, and as it expands, it transfers its pent-up energy of compression into, let's say, it's pushing a box. It transfers that energy into a box. And in the process, the spring is lowering its own internal energy. So a spring, and again, we're considering the spring is the system, expends its pent-up potential energy by accelerating a box. In this case, again, we're viewing the spring as like the system. In thermo, we're going to talk about a system and its surroundings. So the system is losing energy and putting it into its surroundings. The system is doing work on its surroundings. Okay. As a preview, we're going to call this top thing, when you inject work, we're going to call this positive work. And I'm going to write subscripts a lot in this subject. Positive work on system. And the lowercase, we're going to have it be a negative work on system. Actually, I should rewrite this as, in the top case, we're calling the work on the system a positive number. And in the bottom case, any work done is a negative number. Work on system is negative in the bottom case, and positive in the upper case. And this is sort of what you have from Physics 1. If you do work on an object, its kinetic energy increases by W. So if work is positive, kinetic energy goes up. And we will tabulate this in more detail later on. Okay, any questions on the convention so far? Again, this is mostly a review from Physics 1, but we're going to use it for some new things. Okay, so work done during gas expansion compression. Now this is new. So I'm going to give you a quick derivation for the formula for the work done as you squeeze a gas, or the opposite cases as the gas expands and pushes the outside world. We're going to do the squeezing case because it makes more sense. So I'm going to write the answer first. And of course I have broken my pen tip slightly. Okay, so a rough derivation, or I'm going to state the answer first, and it's that when pressure is constant, so this involves like cooling the gas as you compress it so that the pressure doesn't keep going up. Okay, the work done on the gas is negative the pressure, which is being held constant, times the change in volume of the gas. And again, this is like V final minus V initial. Okay, the reason for the minus sign is if delta V is negative, we want the work done on the gas to be positive, because in that case, you're squeezing the gas using the outside world. And that is exactly what happens. If V decreases, then the minus sign makes sure that the work done on the gas is a positive number. So it makes sure that it's an injection of energy into the gas. Conversely, if delta V is positive, so if the gas expands, the work done on the gas is negative, meaning that the gas has used its own energy to do work on the outside world. It loses its energy. Okay, a rough derivation is that the work injected into a system by any force is negative F dot displacement. The negative is there to make sure, or actually I'll let you write this down first before explaining the negative. And I should subscript this, F exerted by system So the work injected into a system is the negative dot product of the force that the system is exerting as it's being compressed, dotted with the displacement. The reason the minus sign is there is that imagine the gas is exerting a force to the right, and I'm pushing to the left to squeeze the gas and compress it. Okay? The dot product of F and X is negative. So the extra negative cancels the negative from the dot product, and you end up with a positive number in the case of the gas trying to expand this way, but you squeeze it, squeeze it, squeeze it. So the negative sign gives us the proper sign conventions here. The reason I have all these subscripts is that the direction of the force exerted by the system and the force felt by whatever is squeezing it are in opposite directions. So if I'm not really careful with my subscripts, I'm going to flip one of my arrows by accident. Okay, but force is pressure times area. Okay, and the pressure has the convention that it goes outward, so I remove the dot product. And area times the change in displacement of the boundary is delta volume, right? If I take a square and I slide it by a bit delta x, the amount of volume changes is the area of the square times however much I translated it by. So this is delta V. So again, this is a rough derivation of where it comes from, but it's not important. At the end of the day, this is important, but with the stipulation, P constant. If P is not constant, just like how in work equals F times delta X, if F changes, we're not allowed to use that formula anymore. We're going to have to integrate. Okay. All right, so if pressure is not held constant over the course of the compression, as usual, we had for work we had F dot delta X. Here for gas we have P dot delta V, or not P times delta V. So we're going to integrate P dV if pressure is not held constant. So calculus version for when P is not constant over the course of the compression. Or I'll just say when P changes over the course of the compression. And it's work on gas equals negative integral of P dV. I ran off the slide a little bit. And you integrate it from V initial to V final. Now, this happens extremely, extremely frequently because, as you might imagine, unless you're cooling the gas at the same time, as you squeeze a gas, its pressure goes up. And as you squeeze it more, its pressure changes even further. So that top formula is not as useful as this formula. Okay, and I'll just remark here, for ideal gases, very often you're going to use the ideal gas law to replace P with nRT over V. So for ideal gases. And at that point, you're integrating 1 over V dV, so you're going to end up with things like natural log of Vf over Vi. And in the case that you're allowing pressure to vary, you're usually going to hold T fixed. The problem would tell you a gas is compressed isothermally, meaning that the pressure is allowed to change, so you have to integrate, but the T is going to be held constant. Okay. And another remark is this is the negative of the area under the P versus V graph. Assuming that the curve goes left to right, so assuming that the integration or the path that the gas follows goes from lower volume to higher volume. If it's the other way, you're going to have to do the negative of the area. Or sorry, the negative of the area. I'll show you an example of this on the next slide. Anybody need more time copying stuff down on this slide? All right. So here we have our first example, and this one's on the homework. A remark is that the homework problem is really gross units. So here I have a gas being compressed from the right to the left. So first, I want you to use just your intuition and understanding of compression versus expansion. Is the work done on the gas positive or negative? Then I want you to compute it using the integral, or the area under the graph, and make sure you get the same sign. Okay? All right, hop to it. Oops. Again, make sure that your calc computation gets the right sign at the end. Make sure you know how to put the minus signs into the hard math version if you need to compare with your intuition. All right, so using our intuition, we have a compression being done. So we know that the work should be positive, right? Compressions correspond to positive work injections. So work on the gas should be positive, and we're just going to make sure that if we use all the hard equations, we know where minus signs go to reproduce what we want. Should be positive. Since it's a compression. Okay, the actual size of the compression it's the negative of the area under the PdV graph. So I have two triangles. Each one has area 1/2 base height. So this shaded green region has area 1/2 times 4 times 1, which is 2. So the green is 2, the other side is 2, so the total area is 4. Okay. But the area assumes that the curve goes from left to right. If the curve goes from right to left, the area variable is actually a -4, right? Because integration backwards, if you want, integration from v equals 3 down to v equals 1 is the negative of integration from 1 to 3. That's two equivalent ways you can see it. Okay, so in the end, we get positive 4 joules of work. And again, this minus sign is because if you have a curve oriented from right to left, the area under the curve is defined to be a negative number. And the instruction is work is the negative of whatever area you get. So curves right to left have area negative. But again, you can always double check with your intuition that a compression happened, so it had to be a positive sign, and it's just up to you to check where you missed it in your calculus. Questions on this example? All right, we're going to do one more before we do the actual first law. Okay, actually. All right, so some reference equations. So we have work is P delta V. So for isochoric processes, delta V is 0. That's the definition of isochoric, no volume change. Again, it's only for isochoric processes which have no volume change. For isobaric, we already covered this. Pressure is held constant, so we are allowed to use negative P delta V. And again, these are specialized to ideal gas processes. The last formulas, they work whether you're compressing a liquid or a solid or a gas. These only work for, or the following equation is only going to work for ideal gas processes, because we will need to write P in terms of volume at every time. Okay, and again, isothermal we're going to derive on the next slide. Again, the rough steps are going to be, you're going to replace P with what it is according to the ideal gas law in terms of volume, and you're going to carry out an integral. Let you guys finish writing. All right, so this is another in-class example. So I want you to compute the work done on a gas during an isothermal expansion/compression. It doesn't matter, it's a volume change. Okay, it's isothermal, so use the ideal gas law because it's an ideal gas being compressed. Good luck. Yeah, what do you need to copy down? Yeah. That's good. I can just tell it to you. Also, can I just say that for the Olympics, the distribution of which sections of the room have signed up is it's 25% middle, 47% left and 25% right. So I guess we are more heavily stacked on the left side, but I did find it pretty funny that it's basically going to be left versus the rest. Answer should involve a log. Okay, so I think you either got it or you got stuck immediately. So again, the clue was to use the work formula, but for an ideal gas, we actually know the pressure in terms of the volume at every instant. Sort of like how when you're doing work equals integral of f dx, you're usually told like, oh, the force is 3x squared, like the force at, you know the force at every position. So you replace f in terms of what it is at each x to actually get an integral you can actually do with the variable you need. Similarly here, we need to write p in terms of a v so we can actually do an integral, so there's actually a v there. Okay, it's an integral of 1 over v. Everything else is constant because it's an isothermal compression. I suppose I didn't use T0, I just used T. Okay, and then I actually wrote these on the equation sheet for you. The log rules, if you have log of something minus log of something else, it's log of the first thing divided by the second thing. Okay, so this is the formula for the work done during an isothermal volume change. Compression or expansion, it doesn't matter. Okay, now I want to do a quick check. I want to check that for compression, the work on the gas is positive, just to make sure I didn't miss a minus sign somewhere. Okay, if it's a compression, Vf is smaller than Vi. So I'm taking the log of a number that's less than 1, like 0.8 or something. Okay. If you remember, log is what power do you need to take e to get that number? So you need to take this to a power smaller than 0. That way you can get a number less than 1, right? E to the 0 is 1, so you need to go lower than 0 to get the smaller number. So this is negative, which cancels with the negative out front to give you a positive answer for compression. I had to wait. So let me repeat that. I want to check that if Vf is smaller than Vi, so compression, I want to verify that I didn't miss a minus sign, and this formula gives me a work that is positive. Okay? So if I just imagine plugging in Vf smaller than Vi, it's saying the work is negative numbers times numbers times numbers times the log of something less than 1. And the log of something less than 1 is already negative. So it's the negative of a negative number, so you get a positive number like you need to. Alternatively, if it's an expansion, so Vf is bigger than Vi, I hope to get a negative number for work done on the gas, because the gas is doing work. In that case, I'm getting the negative of all positive numbers. So all the signs work out as expected. Okay, I'm going to move on to the first law just so we have the conventions done. By the way, I just wrote down the answer here and some equivalent forms. If you replace nRT with PV, I'm not going to have you copy this down. It's on the equation sheet and here. Okay, so the first law, it's your new favorite equation because you're going to be using it a lot. Okay, the rough statement is that the amount that the thermal internal energy of an object changes by, so change in internal energy, and I'll write internal / thermal energy, thermal stored energy maybe. It's equal to the work injected into the object, so I'll write work on object, on system. Plus the heat that is directly injected into the system. For example, if you put the system on a stove, you're directly injecting heat. Okay, it's pretty intuitive. You can increase the stored energy of a system in two ways: by doing work on it, by physically squeezing it or pushing it, or by directing thermal energy into it. The only difference between work and heat is one is mechanical by squeezing, and the other is thermal by literal direct flow of heat energy due to temperature differences. Okay, and the corresponding equation for all these variables is delta E internal / thermal equals work on system plus Q, let me just match my notation here, Q into system. Okay, and this is the equation statement of the first law. Again, what's saying is you can increase internal energy in two ways: by doing work on the system or by putting heat into the system. So relatively intuitive when they're all positive signs. Okay, when there are negative signs involved is when things can get pretty scary. And I put probably 30 exclamation points next to caution because the conventions for this law vary insanely much between individual textbooks, between subject fields, and very often they actually don't even put subscripts on them. They just call them Q and W forever. Okay? And that even causes experienced scientists to perhaps get problems on their exam wrong because they didn't label the subscript. So we're going to leave a ton of subscripts on, and I encourage you to do the same. That way we don't confuse if it's work done on the system or work done by the system. But just be really careful as you go into future classes that they may use work done by the system, which is the negative of the work done on the system in this law. Okay. Okay, so the last thing we'll do is we're going to write a table of sign conventions. Now, I put as a reference the answers up here, like what we're going to fill in. Okay, but I want to write down all the sign conventions for what constitutes positive work, positive heat, positive delta E thermal. Okay, so first, delta E thermal. Oops. Again, some people call this delta E internal. It's the stored energy in the form of molecular motion. A positive delta E thermal means that the object got hotter or gained internal energy. Okay. And I'm going to have to write pretty fast just so I can finish the table, but the answers, like exactly what I'm writing, will be on the next slide, which is posted. Okay? And an example would be if water heats up. So the temperature of water is observed to increase in response to some process. Or ice melts, right? Ice, initially it was bound, you put some heat into it, that broke the bonds and melted the ice. Okay, conversely, if the object loses thermal energy, such as water cools down or water freezes, so it sheds its excess energy and the particles shrink in towards each other and bind into ice. That one's a little bit more complicated to understand. Okay, again, I am going to write fast, so if you didn't finish copying, I'll leave it up, and it will be on the reference slides. Okay, the next thing I want to get the signs straight for are the work done on the system. We already sort of covered this. Positive is when work is done on the system, so a gas is squeezed. And that sort of is the example too. And negative work would be gas expands. Usually it will do work on the outside by pushing a piston or something like that. Okay, and then lastly, heat going into the system. Okay, it's positive if the system is receiving heat from the outside. Such as the system is placed on a stove. Okay, and Q into the system is negative if the system donates its heat somewhere else. For example, if the system is maybe a hot pellet of copper coming out of an oven and you put it into water, the copper injects heat into the system, losing heat in the process. So hot metal donates heat to a water bath. Okay, again, our subscripts do a pretty good job of telling us what is what because I put them on there. But this is just so we're extra clear. All right, again, I'll leave this up. I'll see you Wednesday for continuation of the first law.